last thing we want to talk about is, so we've been talking about KMT and ideal gases, but in fact most gases are not ideal, and their behavior is different than what would be predicted. So here I have a plot of pressure versus number of moles I would expect solving for moles, right? And if I have an ideal gas, the results should be on this line, but in fact you can see that they are way off the line. Okay, so in the real world, the behavior of gases only conforms at relatively high temperature and relatively low pressure. So if I have high temperature, that means my particles are moving really fast. And if I have low pressure, then they're not very compressed, right? So they're going to be free to move about. So, the further apart the gases are and the faster they're moving, the more ideal their behavior, right? But if I compress them, if I put pressure on them, and I slow them down, then they move away from ideal gas behavior, okay? So even a given gas, this is just one gas, at different temperatures behaves quite differently. So why is that? Well, the assumptions made in KMT are that there's negligible volume of gases between molecules. Starts to change if I put pressure on and bring them together, right? Now their volume they take up is less negligible, right? And the other thing that's different than what KMT says is in fact there is some attraction between gas molecules, okay? And that attraction, it usually comes from London dispersion forces, and as we know, the more electrons a compound has, the larger the London dispersion forces, because the larger skewing of the electron cloud that you can have. So there's going to be more attraction when you have bigger molecules, right? Because bigger molecules means more electrons. Okay? And the slower they're moving, the more attraction they can have, right? So if they're lower temperature and higher pressure pushing them together, those attractions will be greater, and the movement from ideal behavior